Okay, let's get back into it. So we last left off starting chapter 5 on system calls. So let's just start reading and go from there. My brain's a little foggy. It's been a tiring week, so um, see what happens. Communicating with the kernel. System calls provide a layer between the hardware and user space processes. This layer serves three primary purposes. First, it provides an abstracted hardware interface for user space. When reading or writing from a file, for example, applications are not concerned with the type of disk, media, or even the type of file system on which the file resides. Second, system calls ensure system security and stability. With the kernel acting as a middleman between system resources and user space, the kernel can arbitrate access based on permissions, users, and other criteria. For example, this this control, this kind of like policy, prevents applications from incorrectly using hardware, stealing other processes' resources, or otherwise doing harm to the system. Finally, a single common layer between user space and the rest of the system allows for the virtualized system provided to processes discussed in Chapter 3, Process Manager. If applications were free to access system resources without the kernel's knowledge, it would be nearly impossible to implement multitasking and virtual memory, and certainly impossible to do so with stability and security. In Linux, system calls are the only means user space has of interfacing with the kernel. They are the only legal entry point into the kernel other than exceptions and traps. Okay, so the system calls provide that safety layer between user space and kernel space. And also it allows the kernel to actually recognize that user space is attempting to access kernel space. So it's that one protection and layer that allows basically user space to not only do stuff with the kernel, but also prevent it from not doing stuff with the kernel. So yeah. Indeed, other interfaces such as device files or /proc are ultimately accessed via system calls. Interestingly, Linux implements far fewer system calls than most systems. This chapter addresses the role and implementation of system calls in Linux. So what are APIs, POSIX, and the C library? Typically, applications are programmed against an application programming interface, or API. They're implemented in user space and not directly to system calls. Okay. This is important because no direct correlation is needed between the interfaces that applications make use of and the actual interface provided by the kernel. An API defines a set of programming interfaces used by the application. Those interfaces can be implemented as a system call, implemented through multiple calls, or implemented without the use of system calls at all. Okay? So the same API can exist on multiple systems and provide the same interface to applications, while the implementation of the API itself can differ greatly from system to system. See Figure 5.1 for example of the relationship between a POSIX API, the C library, and system calls. So the API defines like the definition on what a system call could look like, but it can be implemented differently depending on system to system as long as they maintain that same signature. So for example, you see how this is the implementation itself. This would be like the API, right? The API actually internally makes that internal system call, but basically since this as long as this API has the right signature, basically the declaration in C, from system to system, it can actually be implemented directly, differently. It can actually not have to call a system call. It can actually call something else. So that's why there's like this separation. Okay. One of the more common application programming interfaces in the Unix world is based on the POSIX standard. Technically, POSIX is composed of a series of standards from the IEEE that aim to provide a portable operating system standard roughly based on Unix. Linux strives to be POSIX and SUS v3 compliant where applicable. POSIX is an excellent example of the relationship between APIs and system calls. On most Unix systems, the POSIX-defined API calls have a strong correlation to the system calls. Okay, so they usually map pretty closely. Like the API function names and signatures will usually map pretty close to Unix system calls. So there's a good, strong correspondence. So indeed, the POSIX standard was created to resemble the interfaces provided by earlier Unix systems. On the other hand, some systems that are rather un-Unix, such as Microsoft Windows, offer POSIX-compatible libraries. Wow, there are about 335 system calls. Oh, wow. Okay. Phew. Okay, so the system call interface in Linux, as with most Unix systems, is provided in part by the C library. Okay, so the interface definitions themselves are provided by the C library. Okay, and the C library implements the main API on Unix systems, including the standard C library and the system call interface. So there is some implementation in there. Okay, the C library is used by all C programs, and because of C's nature, is easily wrapped by other programming languages for use in their programs. The C library additionally provides the majority of the POSIX API. So it's all done through the C library. Okay. From the application programmer's point of view, system calls are irrelevant. All the programmer is concerned about is the API. Okay, okay. So as an application developer, we're not really concerned by the exact system calls. We actually do stuff through the API provided by the C library. And it's up to the C library to then invoke those system calls. Okay. So conversely, the kernel is concerned with only with the system calls. Okay, so the kernel is the only one that cares about that. What library calls and applications make use of system calls is not of the kernel's concern. Okay, so the kernel doesn't care about like where it's coming from or how it's being called. All it cares about is its own system calls implementation. So, which is actually kind of just basic object-oriented thinking, I guess. It's like you shouldn't be concerned about how consumers are using you, as long as you provide the mechanism for you to be used. Because if you're providing a mechanism for you to be used, everything is fair game at that point. Okay, so nonetheless, it is important for the kernel to keep track of the potential uses of a system call and keep the system call as general and flexible as possible. A meme related to interfaces in Unix is provide mechanism, not policy. In other words, Unix system calls exist to provide a specific function in an abstract sense. The manner in which the function is used is not any of the kernel's business. Okay, so let's stress this. The manner in which the function, basically the system call, is used is not any of the kernel's business. So how it's being used, the kernel should not care about that. It just knows that it is being used. So Syscalls. System calls, often called syscalls in Unix, are typically accessed via function calls defined in the C library. Okay, they can define 0, 1, or more arguments, which are the inputs, and might result in one or more side effects. For example, writing to a file or copying some data into a provided pointer. System calls also provide a return value of type long. Okay, they provide a return value of type long that signifies success or error. Usually, although not always, a negative return value denotes an error. Okay. So system calls will usually return a number, and usually if it's a negative number, that's going to indicate some sort of error. A return value of 0 is usually, but again, not always, a sign of success. So usually 0 will be good. The C library, when a system call returns an error, writes a special error code into the global error no variable. So we were learning this with headfirst C before, where after a system call errors out, it actually sets that error no variable that we can actually read in to determine what happened. Okay, and then we can turn this into a string. There's like a mapping between the error number and like the specific string. So this variable can be translated into human readable errors via library functions such as peer. Finally, system calls have a defined behavior. For example, the system call getPID is defined to return an integer that is the current process's PID. The implementation of the syscall in the kernel is simple. Basically, it's like a getter. So getPID, define 0, getPID, I guess this means to define, and this is a macro, I think. This is like a C macro defining that this doesn't have arguments, most likely. So no arguments for getPID, and what does it do? It will just get the current TGID, thread group ID. Note that the definition says nothing of the implementation. The kernel must provide the intended behavior of the system call, but is free to do so with whatever implementation it wants, as long as the result is correct. Of course, this system call is as simple as they come, and there are not too many other ways to implement it. So what does syscall define 0 mean? Syscall define 0 is simply a macro that defines a system call with no parameters, hence the 0. So the expanded code looks like this. So basically this macro, this define 0 macro, gets expanded into something that looks like this. So sys getPID. So getPID was defined here. So it's gonna like kind of take that input and then construct this type of function definition or declaration. So since there are no arguments, it's just void. Okay, let's read in more detail how they're actually defined. Okay, so let's look at how system calls are defined. First, note that the ASM linkage modifier on the function definition. This is a directive to tell the compiler to look only on the stack for this function's arguments. Oh, that's cool. So if we decorate the declaration of our function with ASM linkage, it's telling the compiler that the arguments are really only on the stack. Okay, and this is a required modifier for all system calls. So okay, so it's like, so in C we had like things like static and extern and things like that. ASM linkage is probably one of them that kind of gives us the ability to tell the compiler that all our arguments into that function are living in the stack. Okay. So yeah, it's a required modifier for all system calls. So for every single system call that will declare, we need to have this ASM linkage. Second, the function returns a long. So right here, for compatibility between 32 and 64-bit systems, system call is defined to return an int in user space, return a long in the kernel. Interesting. Third, note that the getPID system call is defined as sysgetPID in the kernel. This is the naming convention taken with all system calls in Linux. System call bar is implemented in the kernel as function sysbar. Okay, so the bar system call is really actually called sys_bar. Same thing for the getPID. The getPID system call is actually really internally sys_getPID. System call numbers. In Linux, each system call is assigned a syscall number. This is a unique number that is used to reference a specific system call. When a user space process executes a system call, the syscall number identifies which syscall was executed. The process does not refer to the syscall by name. So underneath the hood, they're all just numbers, like kind of like a table. Okay, so the syscall number is important. When assigned, it cannot change or compiled applications will break. That makes sense. You break backwards compatibility. Likewise, if a system call is removed, its system call number cannot be recycled, or previously compiled code would aim to invoke one system call, but would in reality invoke another. Yep. Backwards compatibility again. Let's see. Linux does provide a not implemented system call. Sys_ni syscall, which does nothing except return enosys, meaning I think error number system. Or you can't have a system call here. Not sure what the semantics of that means. Okay, so the error corresponding to, it's just an error corresponding to an invalid system call. So no sys means invalid. This function is used to plug the hole in the rare event that a syscall is removed or otherwise made unavailable. The kernel keeps a list of all registered system calls in the system call table stored in syscall table. This table is architecture. Huh? Wait, the kernel keeps a list of all registered system calls in the system call table. So those are the numbers to the system calls in the syscall table. This table is architecture. Maybe architecture specific. So there's like different versions for every architecture. Okay, so let's go to this file and see what it looks like, because apparently this table assigns each valid syscall to a unique syscall number. Okay, let's take a look. So it'll be syscall 64C. Syscall 64C. Okay, so we have that, and now we can look at the table. Is that all? This is table is defined. Is it? Oh, it's here. Oh wow. What's NR syscall max? That's quite small. You see this table here? I think this is the table. Right there. Smells like a compiler bug. It doesn't work when the and below is removed. Okay. Interesting. So I'm guessing since they include this UniSTD64 here, that's where we really need to go to. So here we go. So I'm going to the UniSTD64, and this is actually where all the system call numbers are at. I wonder, let's say, let's see what 64 corresponds to. So this is get. Okay. How about, I don't know, what is write? Let's see, F write or something. Oh, write is 1. System call 1. Read is 0. Open is 2. Interesting. Send file 40. Socket is 41. Oh. Okay, so how do we make use of this? Wow, there are a lot of system calls. Let's see how many there are. How many are registered here? I thought I saw like 335 or something like that. Oh, there's a lot. Oh, but it jumps 334 to 424. Okay. So not entirely like consecutive. Probably for like future stuff. Alright. Well, it's defined there. Okay. Let's see. System call performance. System calls in Linux are faster than in many other operating systems. Okay. This is partly because of Linux's fast context switch times. Entering and exiting the kernel is a streamlined and simple affair. The other factor is the simplicity of the system call handler and the individual system calls themselves. Oh yeah, the TGID. Why does get PID return TGID or the thread group ID? In normal processes, the TGID is equal to the PID. With threads, the TGID is the same for all threads in a thread group. This enables the threads to call get PID and get the same PID. Okay. So what's a system call handler? It's going to be like a function to handle the system call. So system call handler. It is not possible for user space applications to execute kernel code directly. Okay, so we know that. They cannot simply make a function call to a method existing in kernel space because the kernel exists in a protected memory space. Okay. Oops. Monitor went off again. Flickering. Okay. If applications could directly read and write to the kernel's address space, system security and stability would be non-existent. That is true. We don't want user space to just willy-nilly go into kernel space, so system calls and their handlers are useful to protect that. So instead, user space applications must somehow signal to the kernel that they want to execute a system call and have the system switch to kernel mode, where the system call can be executed in kernel space by the kernel on behalf of the application. Okay, let's read this again. Instead, user space applications must somehow signal to the kernel. So tell the kernel, hey, I want to do something, right? I want to execute a system call, and then basically say, hey, okay, operating system, instead of executing me in user mode now, can you execute kernel mode on behalf of me? And then where the system call can be executed in kernel space by the kernel on behalf of the application. So yeah. The mechanism to signal the kernel is a software interrupt. And basically, this is how it works. This is how software interrupt works. Incur an exception, and the system will switch to kernel mode and execute the exception handler. So trigger some sort of error and have the system go to kernel mode and run that piece of code to handle the exception. The exception handler in this case is actually the system call handler. Oh, okay, so it's like a fake exception. It's like a fake error. So you throw a fake error and it'll execute the error handler associated with this fake error. It just so happens that this error handler is actually the same pointer to the function that will handle system calls. So the defined software interrupt on the x86 is interrupt number 128, which is incurred via the int 0x80 instruction. It triggers a switch to kernel mode and the execution of exception vector 128. So exception number 128. I don't know why I say vector, but okay. Which is the system call handler. The system call handler is the aptly named function system call. It is architecture dependent. On x86-64, it is implemented in assembly in entry _64.s. Recently, x86 processors added a feature known as sysenter. This feature provides a faster and more specialized way of trapping into a kernel to execute system call than using the int interrupt instruction. So instead of like int 0x80, so right here, instead of like calling this instruction, and this is not like an integer, it's the interrupt instruction. So instead of invoking interrupt instruction at 128, you can just say sysenter, and it'll just do the same thing. Support for this feature was quickly added to the kernel, regardless of how the system call handler is invoked. However, the important notion is that somehow user space causes an exception or trap to enter the kernel. So yeah, the most important thing to know is that in order for user space to do kernel stuff with system calls, it has to execute. It has to force an exception to be thrown, and then the exception handler is actually the system call handler. So, but I wonder, like, how do we know which system call to execute? And I think this is what this next part's about. So, denoting the correct system call. Simply entering kernel space alone is not sufficient because multiple system calls exist. Yep. Okay. So, yeah, you can't just say, okay, I'm going to go kernel mode, execute system call, because there's a lot of system calls. Which system call do we run? All of which enter the kernel in the same manner. Thus, the system call number must be passed into the kernel. On x86, the syscall number is fed to the kernel via the EAX register. So that, if you look into the EAX register, that's where the system call number would be. So before causing the trap, so before we cause an error to the system to execute our system call, the user space sticks in EAX the number corresponding to the desired system call. And then the system call handler then reads the value from EAX. Okay, so it's we need to kind of digest this. Okay, so how to execute system calls. From user space point of view, POV. Okay, so let's say I want to do, I forgot what the system call was for right. Let's say we want to do a system call on close. Okay, so we want to do sys close, right? So it was sys close. We want to do that, and that corresponds to system call 3. So what we do, and forgive me my crappy x86 assembly, I'm learning as I go. So I just basically do some move, right, to move the number 3 to EAX, right? So basically what we want to say is assign 3, which corresponds to sys close, to register EAX. Okay, then what we do is then call sysenter to basically trigger an exception to handle a system call. Okay, then exception runs, exception handler is then what? It's actually the syscall handler. So syscall handler. Okay? Then the syscall handler goes, which system call? Syscall handler. Well, then it looks into EAX, right? And that is 3, which then maps back to sysclose. Okay? So basically this register here contains, like before we even like do the whole system call like exception thing, we have to make sure that we've already assigned the specific system call number to EAX, because that's what's going to be read in order to understand, like for the computer to understand which exact system call is going to actually run. That's how I'm interpreting it as. Okay. Whew. So the system call function checks the validity of the system call number by comparing it to nrsyscalls. So this thing here, if it is larger than or equal to nrsyscalls, the function returns negative enosys. Otherwise, the specified system call is invoked. And this is how we do it. Call syscall table RAX 8. Some assembly instruction. So because each element in the system call table is 64 bits or 8 bytes, the kernel multiplies the given system call number by 4 to arrive at its location in the system call table. On x86-32, the code is similar, with 8 being replaced by 4. See figure 5.2. Okay? So let's say user space wants to execute the read system call. So they call read, the C library calls read, and then it will just make that system call, like the system call handler, and it'll read in and say, okay, well, you want to call sysread, I'll call sysread, and it'll return the value back up the chain here. So simple. Just know that it's like a dance, right? You specify what system call you want, what number you want, and assign it to EAX, because each system call here has like an ID, basically a number associated with it. In this case, if read was used, it would be 0. If close was used, it would be 3. I don't know, dup2, remember dup2? That's 33 here. So yeah, and then you call this system call function, or basically trigger that to happen by throwing an exception or using the sysenter instruction, and then that will just trigger like this whole flow to continue. So parameter passing. So yeah, what happens? We wanna pass some arguments to our system call. What do we do here? Because we know how to set ourselves up for calling a system call now, right? But what about the arguments, the function arguments to it? How do we set ourselves up for that? So yeah, in addition to the system call number, most syscalls require that one or more parameters be passed to them. Okay, remember getPid was just like an exception where we didn't need any parameters, but most other system calls do. So somehow user space must relay the parameters to the kernel during the trap. The easiest way to do this is via the same means as that the system call number is passed. The parameters are stored in registers. Okay, so we had to store all the arguments that we want in our system calls into registers. But what registers? They're actually EBX, ECX, EDX, ESI, and EDI, the first 5 arguments. In the unlikely case of 6 or more arguments, a single register is used to hold a pointer to the user space where all parameters are stored. The return value is sent to user space also via register. On x86 is written into the EAX register. Okay, so what's going on here? So let's say we had a system call, my syscall. And let's just give it some random number. Let's just say it's 555. Okay. Okay, so what we do is basically we kind of assign 555, okay, to EAX, and then we call sysenter. Then basically read trigger, right? It triggers. What was it, a syscall? What was it called? System call. So it triggers system call, and then it'll read EAX, and to determine that it is 555, which then maps to my syscall. Okay. Now, if one argument, say it's like my syscall X, then find in register EBX, right? If two args, find, so that's X, okay? If two args, my syscall, let me just write this neater. It's worth understanding. Okay. If two args where we have my syscall X, Y, I should just, okay, find in reg EBX, which is going to be X, and then ECX, which is going to be Y. So if three args where we have something like my syscall X, Y, Z as our function call, then we'll find it in EBX. Whoa, I keep doing this. Which is going to be what? X, ECX, which is going to be Y, and then what's the next one? It would be in EDX. So EDX, which is going to be Z. Okay, in the case of then 4 arguments, where it looks something like this. X, Y, Z, W, for example, well then we would find X in EBX, Y in ECX. We'll also find Z in EDX, and then ESI, was it ESI? Yeah, ESI would be in W, or W would be in ESI. Okay, now 5 args. What are we looking at here? What is 5 args? So that is going to be in EDI. Okay, so EDI. So my syscall, it's going to be X, Y, Z, W, V. Okay. Whew, that's a big one. It'll be EBX. Okay. ECX will be Y. EDX would be Z. Now ESI would be W. And then EDI would be V. Okay, now we're out of registers at this point and we want 6 args or more. Right? We want 6 args or more. What do we do here? Okay, a single register is used to hold a pointer to user space where all the parameters are stored. So it's just then since these registers are all 8 bytes, 64 bits, it's one of the registers is just going to contain the memory address. So if we had a memory here, right? Memory address, and then let's say 1555 where we have X, Y, Z, W, V, U, for example. Basically we'll just assign EBX to be 1555, and then when we read that, we'll just interpret, our system call will just interpret to kind of just go to 1555 and just start reading off the parameters this way. So, but this part is rare. Okay, so Hardly ever. Mostly it's just these things. And you'll find out why later. Okay. And then results are stored in EAX register. Because at that point, you don't need to know the system call number anymore, right? Because you've already executed it. So you can just overwrite that EAX register. Okay. System call implementation. So the actual implementation of a system call in Linux does not need to be concerned with the behavior of the system call handler. Thus, adding a new system call to Linux is relatively easy. The hard work lies in designing and implementing the system call. Registering it with the kernel is simple. Let's look at the steps involved in writing a new system call for Linux. Ooh, okay. So implementing system calls. The first step in implementing a system call is defining its purpose. What will it do? The sys call should have exactly one purpose. Multiplexing sys calls, a single system call that does wildly different things depending on a flag argument, is discouraged in Linux. Look at IOCTL as an example of what not to do. IOCTL does too much. It's just basically a kitchen sink for all IO operations to a device, if I can recall correctly. So yeah. So what are the new system calls? Arguments, return value, and error codes. So that's what we also have to think about too when we want to implement a system call. The system call should have a clean and simple interface with the smallest number of arguments possible. So yeah, we don't want to do like this whole 6 argument thing. We want to keep the list of arguments pretty small. The semantics and behavior of a system call are important. They must not change because existing applications will come to rely on them. Be forward thinking and consider how the function might change over time. Can new functionality be added to your system call, or will any change require an entirely new function? Can you easily fix bugs without breaking backward compatibility? Maybe system calls provide a flag argument to address forward compatibility. The flag is not used to multiplex different behavior across a system call as mentioned. That is not acceptable, but to enable new functionality and options without breaking backwards compatibility or needing to add a new system call. Okay, so flags that serves like to, trigger different behaviors should still always be in consideration of backwards compatibility. It's not used, you should not be having this mindset to rely on flag arguments where you check specific bits flipped to kind of tuck in functionality that is very different from what the system call actually communicates. So designing the interface with an eye towards the future is important. Are you needlessly limiting the function? Design the system call to be as general as possible. Do not assume its use today will be the same as its use tomorrow. The purpose of the system call will remain constant, but its uses may change. Is the system call portable? Do not make assumptions about an architecture's word size or endianness. Okay, then read chapter 19, portability, discusses these issues. Okay, make sure you are not making poor assumptions that will break the system call in the future. Remember the Unix model: provide mechanism and not policy. When you write a system call, you need to realize the need for portability and robustness, not just today, but in the future. The POSIX Unix system calls have survived this test of time. Most of them are just as useful and applicable today as they were 30 years ago. Okay. Verifying the parameters. Okay, so system calls must carefully verify all their parameters to ensure that they are valid and legal. The system call runs in kernel space. So this is why it's very important to verify input for system calls, because in kernel space, anything can happen and can break your entire system. So if you allow the user to pass an invalid input into the kernel without restraint, the system's security and stability can suffer. For example, file IO syscalls must check whether the file descriptor is valid. Process-related functions must check whether the provided PID is valid. Every parameter must be checked to ensure that it is not just valid and legal, but correct. Processes must not ask the kernel to access resources to which the process does not access. One of the most important checks is the validity of any pointers that the user provides. Imagine if a process could pass any pointer into the kernel, unchecked and warts and all, even passing a pointer to which it did not even have read access. So imagine if a process kind of passed a pointer value that could trigger the kernel to read a memory address in physical memory of a value that belongs to another process. That's like a security issue. So that's why you had to check for these things. Processes could then trick the kernel into copying data for which they did not have access permission, such as data belonging to another process or data mapped unreadable. Before following a pointer into user space, the system must ensure that first, the pointer, so back up, this is what we're reading here. If you have a system call that takes in the pointer value, you have to do these few checks here to ensure that this pointer value is indeed belonging to the process and is valid. And here are like the steps to actually think about and do that to help verify. So first, you need to check that the pointer points to a region of memory in user space. Processes must not be able to trick the kernel into reading data in kernel space on their behalf, right? And remember, like kernel memory address is very fixed. It's usually on the very bottom of the memory space. So if processes are kind of asking to check something in memory that's like around that region, you know something is up, right? So you have to kind of always make sure that when you're accepting pointer values from user space in kernel space, that pointer falls into the region of user space memory. And also that the pointer points to a region of memory in that process's address space. So remember, in the kernel, you have access to physical memory, right? Not the virtual memory address that all the processes sees as their own, right? So you have to kind of check to see that, okay, given this memory address here, does that actually belong to the process? And is that in the process's address space? So the process must not be able to trick the kernel into reading someone else's data. And then finally, if reading, the memory is marked readable. If writing, the memory is marked writable. If executing, the memory is marked executable. The process must not be able to bypass memory access restrictions. So the kernel provides two methods for performing these checks and the desired copy to and from user space. Okay, so the kernel already gives you these helpers to do. Okay, this is interesting. So this way you don't have to write this code yourself. Kernel provides it. So note that the kernel code must never blindly follow a pointer into user space. One of these two methods must always be true or be used. Okay. So for writing into user space, the method copy to user is provided. It takes three parameters. First is the destination memory address of the process's address space, and the second is the source pointer in kernel space. So finally, the third argument is the size in bytes of data to copy. So if we want to copy some data in kernel space back to user space, you have to use this helper here. First argument is basically the destination of the memory address you want to copy to from into user space. And then the second argument is going to be the data in kernel space you want to copy to user space. And then third argument is just going to be the number of bytes that you want to copy. Okay. And then for reading from user space, the method copy from user is analogous to copy to user. The function reads the second parameter into the first parameter. The number of bytes specified is in the third parameter. Okay. So both of these functions return the number of bytes they fail to copy on error. So ideally you want 0. 0 failures. On success they return 0. It is standard for the syscall to return negative e-fault in the case of such an error. Okay. So let's consider an example system call that uses both copy from user and copy to user. The syscall, it's called silly copy, is utterly worthless. It copies data from its first parameter into its second. This is suboptimal in that it involves an intermediate and extraneous copy into kernel space for no gain, but it helps illustrates the point. Okay, so basically we're going to define a system call called silly copy that's going to have 3 arguments. Okay, there'll be the source and the destination pointer, and then also the length to copy. Okay, so copy source. This is basically copy from the user space into kernel space. Yep, into and kernel space is this buffer that lives in there. Okay, and then copy to user will copy whatever is what? Copy from user. No, copy from users. Yeah, user space to kernel space. Copy to user is going to be whatever data is in kernel space back up to user. Okay, so destination is the user. Yeah, so dest here would be the memory address in user space. Buff would be that data, and then len would be the length of that data. And then we just return the amount of bytes that we had copied. Okay, so both copy to user and copy from user may block this occur. Oh, and basically since these return 0 on success, any non-zero value would cause it to be truthy and return these errors here. Okay. Let's do that again. So both copy to user and copy from user may block. This occurs, for example, if the page containing the user data is not in physical memory, but is swapped to disk. In that case, the process sleeps until the page fault handler can bring the page from the swap file on disk into physical memory. A final possible check is for valid permission. In older versions of Linux, it was standard for syscalls that require root privilege to use suser. Okay, so in older versions of Linux, we use this to check to see if that person is root. So it's probably just some if condition that does if suser parentheses. So this function merely checked whether the user was root, and this is now removed and finer grained capabilities is in place. Okay, the new system enables specific access checks on specific resources. A call to capable with the valid capabilities flags returns non-zero if the caller holds the specified capability and 0 otherwise. So capable is a new function call to be able to take in permissions that the user has as arguments, and then your code can check things from there for whatever capable returns. Okay. So for example, capable capsys nice checks whether the caller has the ability to modify nice values of other processes. By default, the super user possesses all capabilities and non-root possesses none. For example, here's the reboot system call. Note how its first step is ensuring that the calling process has capsys reboot. Okay, so that the calling process has capsys reboot. If one conditional statement were removed, any process could. If that one conditional statement was removed, any process could reboot the system. Interesting. Okay, so we just need to get rid of this thing here, because we only trust the super user rebooting the system. And again, defining a system call with 4 arguments: magic 1, magic 2, unsigned in command, and then a pointer to user. Okay. So yeah, this is the check to see to give restrictions on what system calls can be run by what type of users. And the argument here is basically a flag of the capabilities. Okay. All right, I'm gonna stop here. So we'll read. Actually, I want to next time. Let's kind of look at more code like this, and then see if we can like alter some behavior. So, yeah.